Okay, cool. All right, so welcome everyone. Today is going to be our first experimental recording of a conversation about AI, AGI specifically. And today we have my friend Giuliano. We've known each other for a few years now. He studied software engineering at MIT, and I think that's where he got interested in AI and how the brain works. Giuliano, you can correct me if I'm wrong later. He worked at some top companies and as well as startups. And in the meantime, he's been writing a book about creating intelligence. He can tell about it in a second. And yeah, just love talking about with Giuliano about AI. And I think he has some interesting opinions that are divergent from the average or from the usual. Then there's also Alexander, who I met very recently, just at the end of the year, end of 2020, in Moscow. He studied at one of the top schools in Russia and interned at Facebook. Then now he's a research engineer focusing on self-driving cars at Yandex, which is a top company in Russia and one of the few companies working on self-driving cars in that region, if not the only one. Again, you can correct me and add more detail. I think now I talk about AGI with almost every software engineer. And I think Alexander's opinion was quite interesting. I think the main topic for today is, do we need more theoretical breakthroughs to get to AGI? And that's the main topic, but there are also several other related themes that we can touch. And yeah, we'll keep it very super informal, just for friends now. And hopefully we'll just, all of us just enjoy it. All right. Thanks a lot for joining. Please feel free to correct me and add anything else you want about yourself. Giuliano, you want to? Okay, Alexander.
Thank you for the introduction, Tilek, and nice to meet you, Giuliano.
Nice to meet you. Yeah.
Great. Did you guys want to add anything to the intro?
Just want to say that Yandex has a really great reputation among self-driving car researchers. And so I'm impressed that you're working there. Not much added there. I interned at Facebook as well when I was younger. So that's interesting. That's mostly it.
Yeah, thank you. I didn't know about the reputation Yandex has in the US. You mean like the United States, right?
Yeah, exactly. Yeah, I had a friend that he took a self-driving car in Russia, in Moscow, that was like a Yandex. And he was like, oh my God, this is so much better than the ones that we have here. But yeah, Yandex has a really good reputation. And I think Uber... Is it Uber that invested in Yandex or?
Yeah, they did.
Yeah. Anyway.
Yeah, that's cool. Yeah, I think if you use Yandex Taxi, that's what it's called, in Moscow or some other cities, it's the same as Uber. It's the same app. Well, sorry, you can use Uber to call the same taxis, same cars as Yandex Taxi. Cool. Great. So maybe we'll start at the heart of the topic, which I think is a super important topic for our generation. So the question for me is like, when will the AGI happen? Of course, there's also a question of definition of AGI and how to measure it. But I think the main point that we're discussing with Giuliano's main point is we don't need to wait for theoretical breakthroughs. And we're just going to have more compute. It's going to be cheaper, faster, and it's going to happen soon. Please, Giuliano, correct me if I misrepresented your point. And can you just explain this?
Yeah, 100%. So I don't know if the noise in the background is bothering you, because there's some.
What are they
it's
doing?
Fine, yeah.
So yeah, we're basically gonna get to AGI probably in this century. Nick Bostrom, who wrote one of the most important books in the area called Superintelligence, did a research basically asking scientists how long it will take until we get to like superintelligence, right? Like computer intelligence that is as smart as humans. And it like, I think the average was 40 years from now, and it ranged from 20 years to 65 years. So based on researchers' answer is in the century, personally, I believe it's going to be 20 years from now. And that's basically superimposing the number of neurons that we can simulate versus how many neurons we have in our brain. Just 1 second. Let me, sorry.
Yeah,
I just closed down the window because of the noise. So if we look at the number of neurons that we can simulate right now, we can simulate around 1 million neurons, which is the number of neurons that a honeybee has. Now, I think it's even more. I don't know what's the size of the GPT-3. I think it's 200 and something billion parameters, but the number of parameters is the number of connections, not necessarily the number of neurons, right? But in our brain, we have 200 billion neurons. We can simulate, last time that I saw, it was like 1 million neurons. That's like a 200,000x improvement. And we've been doubling the number of neurons that we can simulate every 12 months or something like that. Anyway, doing the math, it would take 20 years basically to simulate the human brain. And then the question is, if we simulate the number of neurons that we have in our brain, can we reproduce human intelligence? And is the software that we have right now capable of simulating the brain? My answer to both of them is yes. We can simulate the software of the brain already with basically backpropagation. And if you look at neural networks, they can basically approximate to any function, right? And so then the question is like, can our brain be represented by a function? And like my answer would be yes as well. There's not much difference between us and other mammals. And if we can simulate what a honeybee, for example, does, so like with 1 million neurons, we have self-driving drones, for example, right? Which is sort of some kind of behavior that animals portray. There are other behaviors that they portray, but when we get to the number of neurons, we probably can simulate. And there's probably a lot of inefficiencies due to evolution, right? So yeah, we're probably gonna get there. I can go into more details, but like another argument is like, oh, let me go over this last one. So one last argument would be, oh, we need some software improvements. And for example, if we look at Go engines, right? They've been improving over time, kind of, if you look at ELO ratings, kind of linearly, which is like an exponential hard problem, which kind of makes sense because you have exponential more hardware. And when you have better software, better algorithms, you have a jump. But if you didn't have it, you still had that linear improvement. So before you just did, a tree search, and then you had a Monte Carlo tree search, and now you have deep learning plus like Monte Carlo tree search. So like that software improved the search, but only with hardware, we would still have Go engines in this decade that would surpass humans. And that's for any kind of task.
Cool. Awesome. I think that's a great start. I think you explained your position pretty well. Alexander, so I know you have an opinion on this. Can
So yeah, I agree that the number of artificial neurons we can simulate is growing very fast, and hardware is improving constantly. But my concern here is that artificial neurons are, in fact, like very different from biological neurons. So like what we have like in most common artificial neural networks, the neuron is a very, very rough approximation of what is going on in the human brain. And for example, like neuron in the computer, in the artificial neural networks, it just like transfers some numbers or doing some floating point operations on numbers, while neurons in the brain are much more complex because they transmit electric signals of different like frequency, intensity. They like can do it in time. And they like interact with each other. And most importantly, as far as I know, biologists, neurobiologists, they don't yet fully understand how brain neurons learn, and they do not understand whether the learning algorithm in the human brain has anything in common with backpropagation, for example. And I think that this can be some important issue while creating this simulation. So even if we have hardware that can process artificial neural networks with the amount of neurons similar to the human brain, maybe some properties of these like human neurons are important. Yeah, and only a part of neurons even transmit electric signals, because like another part of neurons even connect via some chemical substances and so on. So maybe these details are important, and maybe they're important in particular for learning, because what we observe for artificial neural networks is that their learning is somehow different from how humans learn. So people often point out that like artificial neural networks generalize worse, or they need like more examples to learn something. And you need special techniques to overcome this, and they're like cannot generalize from one task to another. And I think that since we do not understand how human brain learns right now, probably we won't be able to simulate it that well, even if we have enough computational power.
Awesome, thanks. That was clear for me. Giuliano, what do you think?
Yeah, I mean, I like the argument as well. So there are a few counter arguments that people may argue, right? So one of them is, okay, is the biological theory, right? So neurons are more complex. We can't explain how they work. I think like one of the rebuttals of that is that apparently some neurobiologists model a neuron as a XOR gate. And basically, I think the way neurons work is that you send a electrical signal, and depending on the intensity, they might send less or more signal to the next neuron or to the other neurons. And the way they model that is with a XOR gate, which can be modeled by a neural network. So even if one neuron, so like what I'm trying to say is that even if one neuron can't simulate a biological neuron, you could have a small network simulating a neuron, right? And I mean, a good analogy would be birds, right? Like birds can fly, and it might look complex. I don't know if you guys are hearing me, because it's connected.
I don't.
Yeah. Birds can fly, and airplanes as well can fly, and they're not as complex as bird wings, but the basic physics behind it is the same. And the basic physics behind artificial neurons and like normal neurons is very similar. Another point is the way the brain functions. So there's actually research showing that there's a theory that some researchers in, I think, University of Portugal, I can send out the links, have been showing that we actually have a process that's very similar to backpropagation, which would be interesting, right? We computer scientists discover a technique that later on was found in our brains. And another question is, okay, even if we did backpropagation, why our models need so much data, right? And in fact, our brains use a lot of data. We learn with a lot of data. Like when we're babies, we're just learning a lot. We're seeing and we're learning. It's just that we get better at learning and we learn to learn. And so there is actually research by one of the DeepMind guys that shows that brains do meta learning, which is learn to learn. So like when you play an Atari game, for example, it becomes easier to play other Atari games. And so this is where software can get better, right? Like right now, we still, like if we learn how if we make a computer learn how a cat looks, we still need to show 1,000 images of a dog for the computer to learn how a dog looks, even though the features are very similar. Cat has 2 eyes, a dog has 2 eyes, they both have tails, and the lower size features are like the common features are similar. We still need to show a lot of images, and that's where software can improve. But even without software improvement, we still have, we can still show a lot of data. And that's where kind of learning in the night kind of is important for humans. So there's actually research showing how important sleeping is for learning. And what I believe is happening is that we're basically compressing our learning through the day and then replaying this and trying to compress that data. One question is, how can we learn? How can we make computers learn with less data? And my answer would be, if computers can generate new data, right? If computers could generate more data, they wouldn't need like data from the real world, because then you can imagine and then you can ask questions, and that's what humans do, right? Like if you show someone that knows what a cat is, shows a dog, the person will ask, oh, okay, like why is what's different from a dog than a cat? And then a human can teach the other person, oh, like a dog, has this type of fur or looks different in this way, and then you can learn. And then you can imagine, and then you can be like, oh, what about this? If a dog has 5 legs, it's still a dog. And then you can learn the boundaries of that function. The problem right now is that the way computers imagine is not well done yet. And I think we will get better. And that's where GANs, for example, work well. And it's interesting because the circuitry that we use for memory recall in our brain is the same for imagination. And in some ways, a GAN, which is a generative adversarial network, which you're basically creating an image, right, is very similar to the way an autoencoder looks. An autoencoder, you're basically getting, for example, an image, and then you're compressing the data into like some small representation and then returning to the real image. A generative adversarial network works in a similar way. You're just not generating the same image necessarily, right? And in our brain, it works the same. And when we have this imaginative software, computers can start asking questions, and they might not need that much data, right? And I think that's where it's going to go. But even without generating data, even with all this data, we can still, generate computers that, drive very well. And one more point about generating data, and I think that's really important. Why is the software that play games the ones that works really well? So like Go engines, chess engines, and things like CarCraft, because the game is a simulated environment, and so you can self-play and learn. With the real world, you can't self-play. And then, like, that's the question, right? Like, oh, could computers, like, play in the real world somehow? Can they generate a real world? And then I think the answer is yes. And the question is just when. When would we'll be able to simulate an environment that computers can interact with each other and learn? And I think, like, that's where, you know, generative adversarial networks, or networks that generate, you know, videos, images, or even worlds will come to play. And I think that's what we're going to see in the next 10 years. We're seeing, you know, like, I think OpenAI just released OpenAI Deal, which generates from text, you can generate images. And we'll see that translate to videos. We're going to see, like, we'll have books that will become videos, you know, will become movies.
Yes. Yeah.
And at some point you can just, like, start imagining text, you know, and then generate videos from that and generate worlds from that. And then you have computers that can self-play and learn from that, you know. And that's why, like, for example, and I think, what's his name? Jan LeCun has this analogy, right? You don't need to drive 10,000 times out of a cliff to learn that you're not supposed to drive out of a cliff. Why? Because we imagine it, right? Like, we imagine, oh, if we drive out of a cliff, we're gonna, like, die. And that's the part that's basically missing. But I think that's what's gonna happen in the next 10 years. When we get more computation, we will be able to generate these worlds. We're going to generate first, you know, text, which GPT-3 can generate, like, text that as good as humans. And then, and what I mean by that is that if you have an essay that's generated by GPT-3 with the biggest models, people can't differentiate that from text that's generated by humans. I mean, human text, if you read the internet, you can see that's a lot of garbage. So it's not a great task. But then we're going to get to images, and then we're going to get to videos, you know, like more complex systems, and then maybe a simulated world, you know, like a video game. And then we will be able to learn. And I think that's the road ahead. In the next 10 years, we're going to simulate more and more environments, and then eventually we'll have self-play. And then it's going to be when we get to AGI.
Awesome. Great. Alexander, you want to add?
It is very interesting that you say about this research that shows that like brain does something similar to backpropagation, because it is very hard to imagine, because like backpropagation is about taking derivatives, and it is very interesting that biology have made something to like do the analogy of this process of taking derivatives. And yeah, I'm very curious to take a look. Actually, I didn't see that. Very interesting. Yeah, and yeah, this is an interesting point about the like people imagining and dreaming about like situations they didn't meet in the real life. Yeah, and I imagine that maybe the network that can like learn on some supervised setting can also like create some unsupervised setting for itself, some distribution of inputs that all look real as well to like improve itself. Yeah, and one more interesting compatibility of the real intelligence is that somehow there are no different stages for training and inference process. So like so the real intelligence, it is constantly learning while doing any task. And do you think we can, how do you think current machine learning advances can simulate something like that? Like no different learning and inference stages, but I think a single like process.
Yeah, that's a good question. I never thought about that. I don't know the answer. I need to think more about that. Yeah, right now we do offline learning, right? Like it's not at the time. That's a great question. Um, I don't know if that's a necessary task to get to AGI, but we like our brains definitely do that. But we spend a lot of time learning in the night. So like when we sleep, clearly we're learning. There's clear research that we are learning during sleep time, right? But during the day we also learn. So like we transform short-term memory to long-term memory in the night. There's hippocampal replay, there's like visual cortex replay, there's all types of replay in our brain, and like we're basically getting like data from lower levels of our brain to the neocortex, which is like the part that is the most abstract, but we still learn during the day. So that's an interesting question.
That's an interesting point, that the sleeping is actually like a completely different phase. You're right, and I didn't thought about that. Yeah, and one more point that I've heard in this context is that I think it will be easier to explain this from an example. So like in my university, I had a probability theory professor, and he once told me that he does not believe in that like current neural networks can lead to AGI. And he explained this because like as far as I remember, like he has a child, and and he also saw like some amount of children from his relatives or something, and he observed that like a child. So he decided to observe like when children start to walk, walking, and he observed that like different parents pay different amount of attention on like how on teaching children to walk. Like some are spending really like a lot of weeks to do this and observe the first steps, and some and other parents are just more busy and they cannot spend so much time. But at the end, like all the children, they start to walk at a similarly like equal age. And like what he concludes from that is that probably it actually doesn't matter that much, like the environment that children like see. So it matters like a bit, but it is not like 100%, or maybe it is not even a 50% of this like learning process, because because of these examples where like different amount of training data didn't matter so much. And what he concludes from that is that maybe some algorithms of learning, or some like maybe reasoning techniques or thought techniques, maybe some language reasoning, it may be somehow built in our brains when we are born. So it is like, so maybe it is somehow encoded in our DNA, and that like learning process from the environment does not actually like create these capabilities, but they are encoded in us when we are born and when we're developing by decoding our DNA. And this DNA, it was also like kind of created from scratch, but by another and much more long process. The process is the evolution. So this is how somehow like some genetic algorithms that for billions and billions years like selected the most effective DNA to for organisms to live. And the problem that can arise here is that like we will be able to simulate this learning capabilities of a human during their lifetime, but maybe we won't be able to simulate this like built-in program. Maybe we won't be able to like make a good enough built-in program for this like brain simulation. What do you think about that?
Yeah, I mean, I agree with the fact that there's a lot of learning that was ingrained in our brain, and like for animals, we call these instincts, right? And we have instincts as well.
Sure.
But still, there are some things that if we're not shown, we don't learn, right? So like, if I never play chess, I'm never gonna learn it. Or if I'm never seen an owl, I will never know what an owl is, or a cat, right? If I've never seen a cat, I will never know what a cat is. But
you'll know the snake. I think there's some animals are there. I think the snake is
that would be scared.
Snakes. I think snakes are there. I think snakes are my understanding. No, that we are afraid of snakes already, like when we're born.
Yeah, I've heard of some like research or something about that. That like even people who didn't ever see a snake, they will be afraid of it.
Yeah, I think there are some general traits, right? If there are big teeth, things like that.
Maybe.
Like you're just afraid of snakes, and you want to say that everyone is afraid of snakes.
No, I'm actually not.
No, I'm joking. I'm joking.
But yes, I think, yeah, I mean, bugs and I think poisonous things, I think some poisonous things. I think some poisonous things people are really bad at recognizing, but some are, I think, are good. Anyways, I'll let Giuliano reply.
That was great. I didn't know that. So even though we don't do the learning during our lifetime, there's a lot of learning that's also passed down. So like going back to Go engines, right? The best Go masters, they didn't learn, like they learned through masters, like they had to go through school and that was passed down. If they had to learn themselves, they wouldn't be as good as they are. And if you actually look at, for example, Go, there were times in history where people got much better and that was passed down. And I think there's 3 eras of like playing Go. It was like in the 20s and then in the 60s, and that knowledge is passed down. So even though you're not necessarily learning your lifetime, that knowledge can be passed down, and it can be, hardware related. So it can be your brain that was programmed to do that in some ways in the gene, or it can be passed down from masters. And that's why like it takes such a long time for Go engines to get so good, because they're they need to self-play all the amount of time that humans actually play, so like the crazy part about computers is that they can self-play much faster than humans. You can accelerate the amount of learning. So even though they're like, I don't know how many years of evolution train our brain, you can still simulate that in a very short amount of time, because you can accelerate with simulation, right? So I think simulation is the most important feature that's going to happen in the next 10 years. And interestingly enough, I don't know if Yandex does that, but Google, with their Waymo self-driving cars, they have simulated worlds where they see and train their car software, right? And they call it like it's not StarCraft, but CarCraft, I think it's called, and it's based on StarCraft. And I would imagine car companies will do that eventually, like self-driving car companies will need to do that, even though you still need to learn from the world. So like Tesla has a lot of data, right, that they can potentially fetch from their cars, from the real world, but still there are a lot of environments that you probably need to simulate for it to learn better.
Yeah.
And robotics it was very important task, right, for robots that grab things, and it's very hard now, but for me it feels like something that could be solved computationally. I think it's just expensive right now to generate those environments.
Exactly. And I think it's just a question of like how expensive it is, and it's going to get cheaper and cheaper. And then, I mean, the other question that Alexander or Tilak can say is like, oh, Moore's law is dead. And like, we can't improve it. And, but in fact, I mean, if you look at processing capability has improved. It's just Intel was mismanaged for some years, and we attach processing power to like what Intel has produced. But if you see the new processors that are actually not Intel based, so like Apple, for example, has the new M1, which is amazing for computers, like much faster. And we're reducing. And there's also like the physical kind of thing. Oh, like you can't get silicon to be this close, but you can stack in 3D and things like that. So anyway.
Do you mean that like processors continue this trend even in terms of, I don't know, like flops per second bound by CPU?
Exactly.
Yeah.
Okay, so you believe in Moore's law, Giuliano?
Yeah.
It will continue.
Yeah.
Got it.
But
Very big one.
What if there are like some, I don't know, physical conditions that will impose an end on this? So, for example,
our brain is in the physical world, right? So we can probably replicate our brain because our brain follows physics laws.
Yeah, that's true. Though my concern here is that like I definitely believe that we can replicate our brain at some point, but like since we talked about this like evolution thing, that probably we need not only like to replicate a structure of a size of the brain for a lifetime, but like for many lifetimes. I'm a kind of a bit afraid to hear that like we like the required computational power will be bigger by many orders of magnitude, and they may like be there are just maybe like too much orders of magnitude that we will meet some like physical constraints.
Yeah, that could be like, that could be one case where it definitely fails, where we can basically physically we can't reproduce the lifetime in of humans, you know, of society in computers. Like I actually need to think about it because I don't know how many humans there were in Earth if you look down, but it's definitely at least 2 or 3 orders of magnitude longer. But I would imagine like passing down as well information from parents to kids is not very efficient. So you know, like I would imagine that learning in, you know, like through genetics is very slow, very slow compared to learning through your lifetime. But yeah, I agree with you.
Yeah, maybe one, but
go ahead.
Yeah, maybe one benefit we can have here is that like this simulation can probably will be able to live like indefinitely long, and they like will not need to encode somehow this information to pass it down to their children. And this may be one point that where they can be more efficient than humans. Yeah. Tilek, please go on.
Yeah, I'm just curious. So Ray Kurzweil spent a lot of time trying to predict when this is going to happen, when AGI is going to happen, and I mean he calls it singularity. And I think his prediction, as far as I remember, for passing the Turing test in under certain definition, is 2029. I don't know if you guys looked into it. Maybe Giuliano, did you look into Ray Kurzweil's prediction and timelines?
Yeah, I haven't, but I think we're already past Turing test. So like if you look at GPT, like tiny, I think even in England, they have the Turing test and it already passed. But like if you look at GPT-3, you can't differentiate the text that GPT-3 writes and a human, the biggest models. That's one example of like an article. I can send out, there's a video of one of the authors showing that that they did, like they randomize, like, oh, show the text of a human and the text of GPT-3, and it couldn't differentiate. And then like the Turing test was passed down, through text. So if you can differentiate text written by humans and then computers right now, then that would mean that I think we passed the Turing test, but then I think we'll move the goalposts. That doesn't mean that the chatbots that you interact with right now, because they're not great right now, doesn't mean that we don't pass the Turing test, because first of all, the chatbots that we interact with, they have a limitation in their model size, just because it doesn't become feasible, to interact with a huge model size, like with the latest and best. But yeah, like we're probably gonna see in the next 4 years, because of computational like power increase, we're gonna, like, the chatbots will catch up with GPT-3 or whatever,
My understanding of a Turing test that it has to be a conversation. I think if you just show text, I understand. I mean, I looked at it like maybe 5 years ago, and there was a question. They showed me, 2 types of text. It's just like a text, and then I tried to guess which one is a human, which one is a robot, and I was wrong many times. that was a cool moment. But I think conversation is so much harder, right? Because you need to come up with the whole like separate life. Like you need to imagine like a persona, who you are, and you have to, I think it's super hard to pass it, and you have to be human enough. You cannot be perfect. You have to have flaws. So it's not just about answering correctly, it's answering the way human would answer. So it's like a modeling a human behavior. I think it's super, super hard. Just modeling human behavior. It's like simulating a whole human. So I don't know. I wouldn't say that we passed the Turing test, in my opinion. I think the text is very easy, no?
But actually, GPT-3, like one of the most common ways of interacting with GPT-3 is through like these conversations. So in particular, since GPT-3 API is not openly accessible, many people interact with it through a system called AI Dungeon. And this system like offers you to have a conversation with GPT-3, and at each step, it provides like all the log of previous phrases in the conversation to the model. So the model like prints a new phrase. And then like you print the new phrase, and then the model, and so on. And these conversations are actually pretty good as well. And one that impressed me lately is that like even a GPT-3 passed a phone screen to Google, because
oh really?
Yeah, there was like a conversation where like GPT-3 was offered to like write very short code for very simple problems, something that companies ask on phone screens, like something like, you have an array and please find, I don't know, please filter out even numbers in this array, or please multiply odd numbers in this array by 2, and like GPT-3 generates a reasonable JavaScript code for that. And like it is not like 100 correct all the time, but it is like often correct, or often like almost correct without maybe one closing curly brace or something. And actually there was even one property of these conversations that I learned recently, and that impressed me very much. And the property is that, so like, for example, you can have a conversation where you ask GPT-3 to solve some mathematical problems or solve mathematical equations or something. And for example, GPT-3 will do it correctly, like, I don't know, in maybe dependent on the complexity of task, but maybe, but say we are given it like some simple tasks, and it is right, like, for example, 70% or 80% of time. And the curious thing is that researchers found that if you So like usually when people interact with GPT-3, they like provide some prompt. Like this is a conversation between, for example, I don't know, like Mike and Jane, and Mike is interviewing Jane, or Mike is asking Jane mathematical questions, and then you like provide an example of Mike's question and Jane's prompt, and so on, and GPT-3 like can generate answers that way. But if we make a change, and for example, we are considering some mathematical problems and giving it to the GPT-3 this way, and it gets the right answer in, I don't know, 70% of time. But curious thing is, if we change this prompt, and if we tell that this is not just a Jane interviewing to Mike for I don't know, some mathematician position, or taking an exam with Mike. But if it is not just a Jane, but if it, for example, a very brilliant, very intelligent girl Jane, if we just add this to the text, GPT-3 starts like generating answers that are like better than average. So maybe if we had 70% of right answers, it can now like generate 85% of right answers. And this like impressed me very much, because we like, when you look at the GPT-3, we like do not even understand like the full compatibility of it, because like it learned, for example, from the books that people can make mistakes. So maybe it like sometimes makes some mistakes to make the text look realistic, because I imagine like a lot of books have a plot when someone is asked some question and is mistaken, and plot like goes so on. But like if we define that GPT-3 need to answer smartly, it gets better. And like we, people didn't even know about this compatibility for several first months of existing GPT-3. And this is like even a little frightening that we don't know it like full compatibility.
Yeah, I mean, one interesting thing is that it might be so much better than humans that we'll probably be able to tell apart GPT-3 than from humans, because it's so much better at answering questions. And so like, it's not gonna pass the Turing test because people will know that it's so much better, you know? But yeah, that was a joke, but yeah, it's interesting, yeah.
I think it would be a cool test. Now that all the interviews are remote during the pandemic, you could write a bot to try to pass the Google or Facebook interview. You would need to generate a good video for system design. That would be incredible. If you could actually draw a system with like a human video.
Yeah, that would be curious.
Not this year, but soon.
Yeah, and software might be automated as well, you know, like right now we're focused on, you know, self-driving cars, and but like even because self-driving cars can move away the jobs from one area to another, but software developers, you know, like even if you look at the way machine GPT-3 was generated, you didn't need 1,000 engineers. You need, 5, 10 engineers, and you need a lot of computational power. And like GPT-3 can generate prompt text, it can generate HTML or web pages and things like that, so we'll see a lot of productivity gains, even in software development. And we think we're special, but we might be, ML might be smarter than us.
Yeah. Though something that a lot of researchers point out, that GPT-3, while it can generate a very realistic texts and even conversations, it often fails at some reasoning tasks. And this is why researchers still don't think that it is like much close to the AGI, because it somehow can do the reasoning that well. So, and what I mean by this is that probably we have passed the Turing test, but we need some like another test for like really a reasoning system for more compatibilities we expect from AGI.
Yeah, like I think the goalposts will move, and they will move, and then we're gonna get to AGI. But yeah, like one of the interesting things, I think there was one of the former co-founders of Parse, which was this software that Facebook company that Facebook bought. He actually wrote down where GPT-3 fails. Like we're gonna find where it fails and where it does well, but it already performs better than humans. Humans also fail, right? There's a interesting quote where, like, let me see if I find it. Basically, it says like humans can write masterpieces. They can paint art. They can do like these amazing things, and that's a human telling a robot, right? Can robots do that? Can robots write Beethoven masterpiece? And then the robot answers, "Can you?" Like a normal human can't write a Mozart masterpiece, right? And so we might be overstating what even humans can do. Like the average human can't pass a Google interview,
Yeah. And maybe we just need to like find these places where GPT-3 is not doing well and add similar things to the data set, and maybe it will start doing better. And though like in general, GPT-3 lacks self-improvement yet. So like this is something that like learning stage and inference stage is still very separated in this system, but maybe this will change like in next GPT models.
And I think it's just like, I think one important task is to simulate stuff. So if we can simulate stuff and then test out, right? Because I think that's what humans do. They simulate, they imagine, and then they ask questions. And so like right now we don't do that, right? Like computer is not gonna ask questions.
Clarifications.
Exactly. And that's where you're drawing the boundaries of a function. Like, oh, this is where cats are, and this is where dogs are. And you can ask, oh, what about this specific example? And then you say, oh, that's a cat. Okay, so you draw the boundary there. But also self-play, and that's where they can just keep learning, like if they can simulate environments and play with themselves.
All right, guys, do you want to add any concluding remarks?
Alexander, go ahead.
Yeah, okay. So I think I've heard like very interesting thoughts from Giuliano. Thank you. Yeah, and like some counter arguments for my concerns about this thought about like that we don't need many new breakthroughs for like creating an AGI, and the main things that we need is hardware. Yeah, so maybe and thank you for like some idea that you mentioned, like about self-play, for example. Yeah, this I didn't think about that, and I think this can be a really important compatibility of such systems in the future.
Awesome. Alexander, do you write anywhere online on this? Do you have like a Medium or Twitter or Telegram?
Not yet, though. I thought about creating a Twitter.
Yeah, cool. I would love to follow. Awesome. And Giuliano, any concluding remarks?
Yeah, that was a great conversation. I also learned a lot of important points about online learning, evolution, environment, playing a role in it. And I also recommend Alexander to write more online, maybe not necessarily on Twitter, but on Medium or anything long form that obviously you have some great ideas and thoughts. So anything that is interesting. I would love to hear, and thank you, Tilak, and both of you for organizing this. This was great. I loved
awesome.
it.
And where can we follow you, Giuliano?
You can follow me on Twitter at Giacaglia. That's my last name. If you look at here, that's my last name. But yeah, I also have YouTube where I also write in Medium. I like to do a lot of stuff. But yeah, I haven't written as much about AGI. I'm working on a book that I'm about to release about AGI and how the human brain works and things like that. I can send out some more information about backpropagation, things like that I mentioned here. So
great, cannot wait for the book. I love your Twitter and I love your YouTube channel. I'm trying to promote it amongst my friends. And I think I've read a couple of your Medium posts on neural networks, which I think are great. All right, thanks so much, guys. I think it was a success. And we finishing right at an hour. I think it would be a good time. Thanks, guys.